All right. Hello, everyone. Hope you guys had a great weekend. Welcome to the second Codebase overview session of Summa Solvency. I'm really thrilled to have you all here. Um, Over the past 2 weeks, we've laid down the foundation with our introductory sessions in zero knowledge proofs, proof of solvency, and then Halo 2. Um, from this week, we encourage active participation from each of you. This is your opportunity to ask questions, share insights, and engage with the code base on a much deeper level. So don't hesitate to ask questions or seek clarifications on any aspect of the code. The residents and the Summa team, they're here to help you. And we've also created a voice channel for the fellows so you can sync up and leverage each other's expertise. And starting next week, our focus will shift towards bug hunting. So, without further ado, let's kick off today's session. And over to you, Enrico.
Okay, right. Thank you, Letty, for the intro. Okay, so we are here again in the code base, Summa Solvency. The last time we focused more on the circuit side. We briefly touched the chip, and today we are gonna go deeper into the three chips that Summa is using. But before, I just want to do an introduction, let's say a recap of what we discussed last time. So I have like 4 files open here that are like, this is the circuit and these 3 are the chips. So these are like the 4 main files that you will work with. And if you remember, like what we said is that the circuit has this trait, circuit trait from Halo2 that is like the only thing that actually Halo2 needs. And this trait has 2 main functions, the configure function and the synthesize function. And in the configure function, what you do, you define the columns, the selectors of your circuit, and you also define the polynomial constraints and the lookup constraint. So this is what the configure function do, and you can follow along here, and you will see that that's what it's doing, and the actual polynomial and lookup constraints are not defined here specifically, but you need to go deeper into the configure function of the chips. So here, for example, or here as well. So that's the role of the configure function. And then there's the synthesize function. That is the one in which actually you basically perform the assignment of your witness. And again, this is a method that is enforced by the circuit trait. And what we do in our implementation is that we leverage, we call them like the category, I call it like assignment functions. So there are like these assignment functions that are written on the chips, and this will help us assign value to the witness. So we can check just one chip, the one that we were describing last time. As we said, we have like the configure function, that is the one that is defining the polynomial and lookup constraints, in this case only polynomial constraints. And this would be called by the configure function of the circuit. And then there are like the assignment function that are, in this case, these two that we're gonna see later. But again, I want to say it again, like the chip by itself is not a Halo2 entity. It's like just something that we created to simplify the code base. So we could call it like I don't know, processor, like whatever. It doesn't need to be called chip. Like chip doesn't exist in the Halo2 core library. like the only thing that exists is this circuit trait that must have configure and synthesize methods implemented. And we can, of course, customize their implementation. So we stopped last time here. So we were like analyzing the configure function of the Mercosur 3 chip. We didn't really got into the logic because I think this is more up to you of this constraint, but we see that we have these constraints that are kind of enforcing some relation between cells, and by default, LO2 will apply these constraints at every vertical shift. But what we don't want it to be the case because we don't want, I don't know, like the cell at column C to always be a Boolean. So in order to solve this issue, we allow to introduce this concept of selector, and by default, the selector is set to 0. So even if this cell is not a Boolean, the constraint will pass. But whenever we actually want to enforce this cell to be a Boolean, what we do is we activate the selector, meaning it goes to 1, meaning that this equation must, well, like for example, in that case, if this is 1, it means that either one of these two factors has to go to 0, which is the constraint of the meaning that this has to be a Boolean. So we now go into the assignment functions. So the assignment function are, let me see. Okay, like the assignment function are used to fill up the advice column with witness values. And in this case, for example, there's this assignment function that is called swap hashes per level. As you recall, the process of hashing, so for each level, the hashing needs to be done following a certain order. So the position of um, the path node and the node that we are hashing. So in this case, we call them the current hash and the sibling hash. The relative position of these two nodes matter because if we hash current hash and sibling hash is different than if we hash sibling hash and current hash. So we need to find a way to enforce that this hashing is performed in the right order. And in order to do so, we use this bit. So it's just like a bit that indicates if we need to swap or not. If I remember correctly, 1, yes, exactly. So 1 means the swap needs to be done, and 0 means that no swap needs to be done. So this assignment function is pretty simple. So we take these 3 assigned cells. So these cells must be already assigned before in the circuit, and we create a region. So we like this layouter is creates a region. So this is like this kind of rectangular shape that you see in the printing of the circuit. And what we do here is interesting. So we basically assign the region using this kind of design, this layout. So in L1, which is this one, we copy the current hash. So we copy this cell and paste it here. And so this copy advisor is also another type of constraint. So if you remember, there are 3 types of constraints. The last one is the copy constraint that is just saying, okay, the cell that is belonging to this row and this column must be equal to the cell in this row at this column. So you're just kind of enforcing that 2 cells in your witness table are the same. And this is how we do that. So this is a bit maybe, at least for me, it was confusing at the beginning because I thought that like all the constraints were written inside the configure function, but actually this is the only type of constraint that is written in the assignment function that is called inside synthesize. But you don't have to worry about that because even if it's written inside the synthesize function, this is still encoded inside the key generation function. So this will be still part of, I call it like the skeleton of the circuit, like the description of the constraints of the circuit, even if it's part of synthesize. So what we do here is like we copy the current hash, the sibling hash. So this is R1, the sibling hash. Then we copy the swap bit here. In the example is 1, but can be 0 or 1. And then what we do here is like we perform some operation that this is not a operation that is performed inside the circuit, but we're just saying, okay, if this is 1, then return me the swap. If this is 0, then do not perform any swap. And in the next row, so as you see now, we're operating on offset 1, while before we were operating offset 2. We then assign the this result basically. So we basically assign the result of the swapping. And I mean, this is kind of pretty straightforward. There's no crazy logic here. But the important thing that you need to see is that also in the assignment function, this is where we enable the selector. So by enabling this selector inside this region, we make sure that the constraints that are kind of enforced by this selector are activated. So in this case, you see that the ball and swap selector enforce these two constraints. So every time we call this assignment function, we're gonna activate the selector, and therefore these two checks will be performed. Otherwise, again, I say it again, but it's important that the selector otherwise will go to 0, so there will not be any bool constraint or swap constraint. And lastly, we return the swapped cells, and because we are gonna use them later inside the circuit, so you will see that like we call this assignment function inside the main circuit here. So for every level, we need to perform this swapping according to the swap bit. And the swap bit, of course, is not always the same, but for each level, there's a swap bit. This swap bit level that is coming from path indices. So this is the first assignment function. And there's another assignment function inside the Merkle sum to chip that probably is even simpler. And this is the one that is just performing the summation. So we pass two balances. Since we are not using the let's say the Merkle sum tree that has this property that you also need to do hashing balance left, balance right. We are just performing the hash of the sum of the balance, so we don't need to swap the balance. So that's actually a constraint that we removed last week because it was like an over constraint. It was doing a swapping when there was no need to do a swapping on the balances because it was a leftover from the previous implementation. So this assignment function is simply taking two balances as input, and you are like copying the balance, the current balance, copying the element balance, performing the summation. So this is performing the summation outside of the circuit. So these are like when I say outside of the circuit, means that this is like a Rust code that is just performing an operation, but it's not setting any constraints. While we take the sum, we assign it to the sum cell. So the sum cell would be, you see, column advice 2, offset 0. So this is the cell where the sum gets assigned. And yeah, and again, important is that we must enable this sum selector to enforce this constraint. So the sum selector is the one that activates this sum constraint, and this is like the simplest constraint ever, probably. It's just saying left plus right minus computed sum equals 0, meaning left plus right equals computed sum. So these are like the assignment function of the chip, and I will stop if there's any question before I want to say something that is important. Okay, no
I guess
question.
there are no questions. Oh, we do have one.
Yeah, I see. When computing the sum, do we also need a range check? Okay, so the yes, probably you do, but the thing that you guys need to realize is that these chips are kind of independent components. So like the range check, yes, is performed on the balances, but this is performed by another chip, and they all come together inside this circuit. So like I show you when this is performed. So mm, let me see. So here is when you do like some balances per level. So this is the assignment function that we just saw. And the range check is performed here. So as you see, each balance cell is constrained to be within the range. So the range check is not performed directly inside this function, but is performed yeah, on the same values, but inside the circuit by another chip. Is some balances per level newly added? Where is some balances per level? Newly added, you mean it's a new part of the code base, right? Yeah, I think so, because like as I mentioned, like while I was preparing the presentation last week, I realized that yes, I realized that we were like doing some extra work on the balance that it wasn't needed. So before, I think it was called swap balances per level, that it was both performing the summation and the swap. But as I said, since we moved to this broken Merkle tree, we don't need to swap the balances anymore. So that's why I kind of simplified the constraint. So now it's only performing the summation and and not the not the swap. Okay. So
I've got
what I
one more
wanted to
question, Enrico.
yes, go ahead.
Do we do a rain check on the sum as well,
No,
or
no,
do
no,
we
no, no.
do it only on the balance?
Yes, exactly. So we do the rain check on basically on all of the input balances that we pass to the circuit. So
Mm-hmm.
um, if you see like the inputs of the circuit are like the entry and well basically like the input balances are the balance of the entry and the balance of the sibling nodes. So we do the range check only of the entry balance and the sibling node balance, because these are the only balances that are coming from outside, while the
Oh, okay.
sum
Hmm.
is performed inside the circuit. So we can kind of forecast that if I don't know, if all the input of the summation are like 4 bytes, the sum which is performed and constrained inside the circuit will never overflow the prime. So it's kind of, we could do the range check on the sum, but it would be like an extra constraint that is not needed, at least in my opinion.
Got it. Got it. Okay.
Okay, cool. So what I wanted to tell you now is something that was also kind of tricky to me when first learning LO2, is that like, okay, but how, if you already provided like this assignment function, how can someone like generate a malicious proof, or how can you attack the system? Because, you know, like this API is already kind of enforcing that, you know, you perform the summation. So like this API is already doing the summation by yourself. Like, why do you need a constraint, or how can this constraint not be met? Because if we use our own APIs, it will always be the case that this cell will be like the sum of these two cells. So the explanation of that is that a malicious prover is not really using your own APIs. Like you you can take the skeleton of the circuit that is defined by the verification key and the proving key, and this skeleton encodes all the constraint, and then you can fill the witness. Think about it like filling it manually. So you can basically filling each cell with a value that you pass as a malicious prover, and you don't need to go through our assignment APIs. So that's how you can exploit an under constraint circuit. And for that, I encourage you to watch the presentation from CC, from PSC, that is explaining this concept in a very good way. And I think he calls it like the evil prover, the one that is trying to exploit another constraint circuit. And this is a really important concept. So in the way I see that is that, okay, you as a circuit developer, as me as like a Summa developer, I will generate these artifacts, these keys, like the proving keys and the verification key, that are kind of encoding some things like the table size, what are like the columns, what are like the size of each subregion. It will contain the polynomial constraint. It will contain the lookup constraint. It will tell when the selectors are activated or not. It will tell also the copy constraints. But then the assignment of the advice columns of the witness, yeah, you can use our own APIs because they make it simpler to fill this kind of very, very big table. But you can also think, if you need to put yourself in the mind of someone that wants to exploit this circuit, is that you can fill it in whatever means you have at your disposal. You can pick manually filled elements and fill it inside the cells. So I think this will be also a very good like tooling if for auditors. So if you can kind of fill this witness manually without passing through our own APIs, because even for us, it's difficult to reproduce some error, like to test for some errors, because we have our own APIs and they are kind of made to not generate this error, if I kind of explain myself. is this the video? Yes, this is the video. So there are like two videos. There's like this one and also another presentation that he did on Bogota last year, 2 years ago, and they are kind of same idea. Bogota is shorter, but yeah, that's the video. Yes, correct, Ali. Yeah, that's a good point. Okay, so this was the end for the Merkle Sum 3 chip. I think we are on time, so I'm gonna go through the range check chip. The range check chip is important because it allows us to constrain that some value is inside a certain range, and therefore to avoid the risk of overflow. Well, you will tell me if we are actually avoiding this risk, but I think so. So this okay, let's take another approach here. Maybe it's easier, or maybe it's more logical if we start with like the constraint and then we go inside the logic and the assignment function. So this is can I close this? This is the configure function, okay? So again, we have a selector that is this lookup enable selector, and the operation that it's doing is taking some cell. So whenever the selector is activating, it will query the cell inside this column, inside this advice column Z at the current rotation, and we will also query the cell at column Z at the next rotation. So it will be like the next row relative to the selector. And it will also query this fixed table. So this is like you see, this is a fixed table, and you will see this inside the circuit logic, but this table is filled up with values from 0 to 2 to the 8 minus 1. So it's covering all the values that are in a byte range. Then this constraint is computing the difference between z car, so this cell, and the next cell multiplied by basically 200, like 2 to the power of 8, and this is equal to yeah, like a left shift of one byte. And whenever this selector is enabled, then the constraint that we are enforcing is that this difference, so this diff value, belongs to this U8 range. So like belongs is simply like we call it lookup because this is actually a lookup. So you take one value, you take a table of possible values, and the lookup is saying that is the value included in the lookup table. So this is the constraint. So I kind of intentionally started from here because like maybe for you it doesn't make sense. Like you don't yet understand what's the logic of this being able to constrain that a value is inside some byte range. But this is actually the only thing that matters from the circuit perspective. So they only like the circuit is only understanding and parsing this lookup constraint, and then we build the logic on top of that. So now I'm gonna explain you like the actual logic. So the actual logic is explained here. So in this example, we have this value, that this is the value that we want to constrain. We want to constrain this value to be within the 4 bytes range. So what we do is basically we we decompose the value inside in bytes. So we take all the bytes representation of this, and we kind of do this kind of sequential operation of subtracting the the least significant byte from our value, and then we do this divided by 2 to the power of 8. So it's like right right shift of 1 byte. So we do this once, twice, 3, 4 times, and in this case we end up with 0. So what are like the constraints that we need to enforce? So first of all, we enforce the constraint that I mentioned before, that like this value minus this value when right left shifted by 1 byte, so it will become like this. So the subtraction between this one and this one belongs to the lookup table. So it will basically mean that like 0x for f belongs to the lookup table, and it means that 0x for f is a byte. So it's not greater than a byte. And the second constraint, the second very important constraint that we need to enable is that the last decomposition is equal to 0. Because you can, like, maybe a good way to think about the why of these constraints is thinking about like an adversarial case. So if let's say we want to check that this value is inside of 4 bytes. So we will do like this progressive subtraction and dividing, subtraction and dividing, subtraction and dividing. And in this case, this constraint will be satisfied because we see that the amount that we subtract is actually a byte, is inside a byte. So this subtraction will hold. This constraint will hold, but the second constraint will not hold because at the end of this operation, we will have a value that is not 0. So this means that the value that we range check is not inside 4 bytes. And the other type of attack that you can potentially see, so let's say that we have something like this. So we have a value that is not in the byte range, but we want somehow to trick the system. We want to try to pass the constraint anyhow. So in that case, this if this is the witness table, okay, maybe I ask you the question, like why this will fail? Like if we use this this witness, like in which point the constraint will not pass? Okay, then I will answer this question. But first, if someone can tell me like why this is not passing.
By not passing, Enrico, you mean this is not actually effective, or?
No, yes, I'm saying that if I fill up the advice column with these values, so this value is not in the 4 bytes range. So we expect the circuit to throw an error, to not pass a constraint, to not satisfy a constraint. So what I'm asking is like, yeah, 5F is intention. Yeah. That's actually why it should fail. Okay, I will answer if you. Yes, exactly. That's the right question, the right answer. So when you subtract, so actually this will be like, okay, this is actually I think also the answer of your same question. So if you were subtracting this, yeah, you need to subtract and then and then and then divide by 2 to the 8. So you need to no, so sorry. You need to first multiply this by 2 to the 8. So you need to left shift it by 1 byte and then subtract. And then the result of the subtraction will be this, which is not in a byte. So that's why the constraint will not pass. And yeah, like we also provide the assignment function for this region. So the assignment function will take a value like this. So this was for f, and this is passing. And the assignment function will perform this decomposition. So will perform this these operations basically. And you will see that we only take as input one value, the assigned cell, and then this whole thing is like performing this decomposition outside of the circuit, I would say, as an operation, and then it will assign this z next val that is like this for each loop. And the most important thing that I think is also a kind of a copy constraint. So we are like saying that the last cell of this z column must be equal to 0. And in this case, this is a copy constraint between a cell in the advice column and a cell inside this fixed column that is constant. So this is also something that is that must be known during key generation. And during key generation, we will fill this fixed column with a value that is 0. And here we're like making sure that the last value in this column is actually equal to 0. Yeah, that's what I wanted to. This actually mean? Yeah, that's correct. Okay. Then the last chip that we have is Poseidon. So the important thing, and I mean it's also I think good for you, but we didn't have to reinvent the Poseidon chip here. We're like actually underneath using this gadget from Halo 2 gadgets, and it would be interesting to learn if this was audited or not. But I was checking the history, and this is something even if we are using the PSC fork, the original Poseidon chip was already in the Zcash fork. So I assume that if the Zcash fork was audited, this will kind of also pass the audit to the PSC fork, even if it's using a different curve. But I'm not sure about that, honestly. So, like, I want to explain you what is Summa doing with this Poseidon, and why, like, what we are adding on top of the Poseidon implementation of Elo2 gadget. So the Poseidon provided by Elo2 gadget has some specification that makes it kind of more customizable. So if you know a bit about Poseidon, there's like some parameters that needs to be instantiated for a Poseidon implementation, and these are like width and rate. So this is something very specific that I'm also like not super familiar with the logic of Poseidon, but these are like details of the implementation of Poseidon, and this basically is defined inside this spec. So as you can see, this, for example, here, this is the configure function on the POW5 chip. That is the one coming from Elo2 gadgets. And this requires to define this specification. So this is like a trait that must be defined to this chip. And we define this here. So you will see that we define our own Poseidon specification. And the specification that we define takes some hard-coded value. So these two, so if you see, like we define a width of 2, we define a rate of 1, we define the full rounds, the partial rounds, and we also define the constants. So the constants, you will find them here. Then the constants are generating using a script. And actually, we also have the script. Python. So we have like this Python script to generate the parameters that we created our own script, but it's basically like if you check these links, they give you a better understanding of how and why these parameters are generated. But what I think what you should focus on during the audit, because this is an open question for us as well, is that are our specifications, so setting like 2 as a width and 1 as a rate, secure given the length of the input of the usher. So I'm not sure if this is as like the number of inputs has some influence on the security, or if this is already accounted for in the gadget. But I think this is something that is yeah, this should be taken into account during the audit, because we basically took an existing for example, if you see here, we in the comment, like you said, pattern after this, and there's like another implementation of the Poseidon hashing, but this one is using like 3 and 2 as width and rate. So why we chose not to use 3 and 2, we chose 2 and 1? Because in this way, we use less advice columns and less fixed columns. So this was like the reason of using that was for efficiency, but we're not sure that like the trade-off is means less security during the Poseidon. So if some of you has a good understanding of Poseidon, it would be very interesting to have an assessment of the security of this implementation. And again, like we are not touching the actual Poseidon implementation. So you will see that this configure function is coming from the chip, and also the hash function is coming from the chip, from Elo2 gadget. We are only adding the specification, and the thing here is not to add it to audit the gadget from Elo to gadgets, but to see if the gadget plus the specification of Summa have some security issue. So this was the last chip. I see there are some questions. Okay. Okay, I think that yeah, there's still some confusion on the range check. Maybe I can go through that. Yeah, I see. Okay, let's go through it again. So we have a value. Okay, we need to range check this to be in 4 bytes. So what we do first is like decomposing it into bytes, and then we keep subtracting this. So this will be like okay, let's do like this, because maybe that was the question, like why we need to divide. So that will be if we don't do like the right shift, that will be the result. So if we keep doing that, we don't satisfy the other constraint. So if we subtract this, then in this first level, the constraint is satisfied, because this minus this is actually, well, this multiplied by 2 to the 8 is actually satisfying the constraint, okay? But if we keep doing this for the next constraint, for the next row, this constraint will not be satisfied. So what we do instead is that we subtract, and then we left shift by 1 byte, and we keep doing that. And the constraint that we set is that this, okay, so this is what I described right now is just the logic of the assignment. This is not the constraint. Well, the constraint will say that, okay, at this row, let's say we activate the, it's called lookup enable selector. This will check that this value minus the right shift of this, so minus this, which will be equal to 0x4x, belongs to the lookup UA table. And this will be applied here, activate, here we activate the selector, here we activate the selector, but here, notice that we don't activate the selector. Like at this row, we cannot activate the selector because there's no next row where we can perform the subtraction, etc. So like this next row will be, think at it like being a 0. So if we activate the selector here, if we do like 0x00 minus blah blah blah, we don't need to do that. Probably it will still pass the constraint, but we don't need to activate this here. So we just activate the selector for from the cell at row 0 until the cell at row n bytes minus 1. And this is, you can see this here. So this is where we enable the selector. Can you take the example where z, okay, yeah. So the example 5f. This is the example where we don't want, since the value is not inside 4 bytes, the circuit should throw an error, should not pass the constraint. So in that case, we'll do like this. So there's like 2 ways in which this can fail. First of all, we perform the subtraction. We have time, right? Yeah. I will just write it down. Okay, this is the first case. So we decompose actually the value correctly in bytes, and we keep subtracting and dividing correctly. So in this case, this lookup selector will pass, this will pass, this will pass, this will pass, but, well, I mean, let me fix this. This would be this. But this will not pass. So this is different from 0. So this will fail. Okay. The other case, that is the other one that I mentioned, is that what if we try to here subtract 4f, cf, and then we do like this, do like this. So in this case, what we do here is 2f. I think I'm yeah. Okay, so here we subtract this by 0, x, 1f, 2f, 3f, 0, 0. So remember like that the logic of the constraint is that you take this value, so at the cell corresponding at the row where the selector is activated, and then you subtract it by the next cell, right shifted by 1 byte. So in this case, this would be the subtraction, and this would be like something that doesn't belong to the lookup table. So I'm not able now to do the subtraction here live, but you will see that this subtraction doesn't belong to the lookup table, and therefore the constraint will fail. Okay. I hope that I explain it correctly, but if you try do it on your own, you will see why this makes sense. And also you can see that here, okay, I think this was deleted, but there used to be here a chip that was actually using this logic. And last thing that I want to say is that probably like the last thing that I want to say is that this is not the only way to do range check. There are other ways, and we used to do it in another way, but this is like the way we do it is very efficient because it doesn't create constraints, like polynomial constraints of high degree that would be like expensive. But I think if you check in a Halo2 example, like this repository from IceMelon, you will see another way of doing range check. So it would be also cool if you can check different ways of doing range check and what are like the trade-off there in terms of performance. Okay, it's all for me.
Do we have any more questions? I see Ali has a question. Yeah, Ali, go ahead.
Yeah. Thanks, Enrico. This was excellent. I'm just wondering what is wrong with doing a range check, like straight up take the balance as a field element and assert that it's less than or equal to the prime divided by the number of leaves times log of the height of the tree. Is it because it's expensive constraint wise, or just
Okay,
wondering?
yeah, I mean, like this is kind of actually what we are doing. So we are like okay, what you're suggesting is just saying, okay, this is the number of levels in the tree, and this is the number of leaves. So in order to, we know that this is the prime of the circuit. So if we know that like this balance is in it must be maximum like 2 bytes or a specific number in order to not overflow the circuit. So in order that the summation is not overflowing the prime when computed inside the circuit. So this is actually something similar to what we are doing. So first of all, we don't need to necessarily account for the maximum possible that this value can be, but sometimes is enough given the range of the balances inside the custodian to not range check them to the maximum value possible. So potentially, like in our implementation, we set 8 bytes. Okay, so in theory, the balance could be greater. They could be like 14 bytes and still not overflow. But there's no really case in which this balance is like there are like user with a balance of like 14 bytes. So we don't need to go like that far, but we can do it like a smaller range check. And the reason why we do this decomposition, so let's take the other case. Like let's say that the value is, I don't know. We said that a value is 8 bytes and we want to check that balance is between 0 and is in 8 bytes. What we can do is like fill up the lookup table with these values and directly well, actually this is just 1 byte. So this would be like 2 to the 64 minus 1. So we can naively create a lookup table with all the values from 2 to the 64, from 0 to 2 to the 64 minus 1. But yeah, we can do that. But in practice, we cannot because like this is too big of a lookup table to be supported by by LO2. So I think we can get without running out of memory until like 2 to the 26, 27. So we cannot create a lookup table that is this big. So because of that, we need to chunk the balance in smaller components, and then we range check each of the component, each of the decomposition of the balance, and we check that the decomposition is performed correctly. And by the way,
But
like
is
this idea of, yeah,
sorry, Enrico, is doing it the lookup route the only way? Like, I'm just wondering what is wrong with vanilla assert balance is less than or equal. Does it generate underneath? Does it turn into a huge number of constraints? Is that the reason?
I mean, this is what we're doing. Like the range check is this thing. What do you mean vanilla assert? Like,
Like you take the balance as a field element and you assert, you create a constraint that it's less than, or when you subtract it from the maximum, or you subtract the maximum from it, the result is positive or something like that. So like a single assertion
uh,
as opposed to doing a lookup. I agree with you that doing a lookup
okay,
or
yeah. Okay, I understand the question. Okay, yeah. So I mean, we could not. Okay, this is interesting. Like what you're suggesting is like taking balance and saying less than this one. Uh, yeah, I think we can do that. But if you look underneath the way that you do the lookup, sorry, that you do the less than is actually using lookup. So the logic behind it will be the same. And the other way that you can do less than, that is the one that is applied in Circom, for example, that is doesn't support lookup table, is doing like a bit decomposition of each value. So you need to decompose balance in its bits representation. You need to decompose this value inside its bit representation, and then you check that basically you run from the most significant bit to the least significant bit, and you check that the one is greater than the other using this bit decomposition. So if you were
yeah.
doing this less than assertion, you would be still doing lookup in a way.
Yeah, that makes sense. Yeah. Um, so because eventually underneath everything has to be molded into that Planckish equation. So there is no such thing as less than that can be asserted in that basic equation. It has to be simulated somehow. So yeah, as you said, it turns into you use these bit decomposition to achieve that basically. So yeah. So the short answer
Yes,
is,
and
as you said, yeah, it turns out to be more expensive if we do it less than. It will be translated underneath into something more, even more constrained, probably.
do you see also my other tabs, or is just GitHub? Well, like VS Code.
Only this one.
Okay, I want to share with you. Well, I will share with you this repo later, but the repo that I refer to is doing the range checks in different ways. Is also doing it with like bit decomposition. So you can check this out. Like there are like many ways to do this range check. I will take these last two questions if you guys have time. So we only constrain balances to only 2 to the 64, but since iter's balances are 18 decimals, wouldn't that overflow easily? Okay, good question. Like of course, like what we are doing here is like that everything is like we don't really have the concept of decimals inside the circuit, so everything will be turned into a field element. So the reality is that when you check like your balance inside an exchange, you don't have this notion of decimals. So you cannot buy the 18th, let's say the 18th decimal of Ethereum, of Ether, but you can only buy a fraction up to a certain point. So that's the practical reason. And even actually, if you were considering 18 decimals, like check that like 2 to the 64, 2 to the a power of 64 is actually a very, very big number. So I don't know if there are like people with such a big balance, even considering the 18 decimals. But this is like also a question related to the implementation. So one can set an higher range check if they want, so it's okay. Why not right shift by 64 and range check only once? Because if we right shift by 64 only once, we need to do a lookup with a range table that is filled by values from 0 until 2 to the 64 minus 1, and we cannot support that.
All right, that's a wrap. Those were really interesting questions, and I highly encourage the fellows to put more questions in the Discord. And I'm sure the Summa team will do its best to answer it. And thank you, Enrico. That was a really great presentation. And thank you, everyone. See you all in the next session. Bye bye.
Bye bye.